Welcome back to the Deep Dive, where we take your essential source material and turn massive stacks of research into immediately clear, useful knowledge for you.
And today we are deep diving into maybe the most foundational type of data on the planet.
The spreadsheet, that simple row and column structure we call tabular data.
Right. It's, the invisible backbone of the modern world. If you're in biomedicine, economics, climate science, supply chains, you're living in tables.
And the goal is always prediction, right? Filling in a blank, classifying something.
Always. Predicting a biomedical risk, deciding which drug compound to test next, that's the core task.
And for decades, I mean, we're talking 2 full decades, if you wanted top performance on that kind of data, you used one thing.
Tree-based models, absolutely.
Yeah.
Your gradient-boosted decision trees, the XGBoost, the CatBoosts, they were the undisputed champions.
Why, though? Why did they dominate for so long when deep learning was transforming, images and text?
Because tabular data is fundamentally messy. It's just specialized. We call it heterogeneous.
So lots of different kinds of stuff all mixed together.
Exactly. Columns have different scales, different data types, and they're almost always riddled with missing values, with outliers. Standard deep learning just couldn't handle that chaos.
But our sources today are all about a radical challenger, a foundation model built specifically to master the spreadsheet.
The Tabular Prior Data Fitted Network, or TAB-PFN.
It's a generative transformer-based model, and it seems like it's here to completely disrupt that hierarchy, especially for small to medium data sets.
And the initial finding, the thing that grabbed our attention, is just stunning.
Go on.
In the benchmarks, TAB-PFN gets better performance in a classification task in just 2.8 seconds
Okay.
than an entire ensemble of the strongest baselines, including CatBoost, that were given 4 hours of tuning time.
Wait, hold on. Say that again. 4 hours versus 2.8 seconds?
4 hours, a whole afternoon of compute time.
That's not just an improvement. That's a total paradigm shift. I mean, the idea that state-of-the-art accuracy is now basically instant right out of the box, that's the whole story right there.
And the speed isn't just about a faster chip. It's a conceptual shift. TAB-PFN is described not as a prediction algorithm, but as a learning algorithm that is itself learned.
Okay, let's unpack that. That sounds complicated. So standard deep learning trains a model on a specific data set, right?
Per data set, yes. You feed it data, it adjusts its weights, its parameters over and over again to get better at that one task.
So how does TAB-PFN flip that?
TAB-PFN was trained once, offline, across millions of different synthetic data sets. So when you bring it your new unseen data, it gets the entire thing.
The whole spreadsheet.
The whole thing. Labeled training samples, unlabeled test samples, and it does the training and the prediction in one single lightning fast forward pass.
So the magic is that the data set you give it becomes its immediate context, which sounds a lot like in-context learning.
Precisely. It's the exact same mechanism that makes large language models so powerful, ICL. The model isn't changing its internal weights to learn your data.
Right.
Instead, it's using this massive pre-training knowledge, its prior, to figure out the best way to make a prediction instantly, just based on the examples you just showed it.
So the network has learned a kind of universal meta-algorithm. It knows how to approximate really complex methods, almost like Bayesian prediction, just by looking at your data once.
That's a perfect way to put it. The designers stopped writing explicit instructions and instead focused on creating the perfect training universe so the model could discover the algorithm on its own.
And the sweet spot for this is what? Data sets up to about 10,000 samples?
Up to 10,000 samples and 500 features, which is crucial because that covers something like over 75% of the data sets on popular ML benchmarking sites.
So for most people doing day-to-day data science, this is their new baseline.
It should be. But that raises a big question. If the model needs to learn a universal algorithm, where did it get all that experience? You can't just feed it a few public data sets.
Right, which brings us to the secret sauce. This synthetic universe of spreadsheets they created. Why couldn't they just use real-world public data?
Well, for one, public data sets are often small. But the real danger is data contamination.
You mean if the model sees the test data during training?
Exactly. If that happens, its performance looks great, but it won't translate to new, real-world problems. They needed a massive, clean, and endlessly varied source of data.
And when you say massive, you mean?
Around 100 million synthetic data sets for a single training run.
Wow.
And they did it using something called structural causal models, or SCMs.
Okay, SCMs. Give us an analogy.
Think of it like building a hyper-realistic flight simulator. You're not just taking photos of real planes. You are modeling the underlying physics, the causality of lift, drag, thrust, the rules of the universe.
Got it. So they model the underlying rules that create real-world data instead of just copying the data itself.
Exactly. SCMs give them a formal way to represent those causal links, so they could generate endlessly diverse, yet statistically grounded practice problems for the model to solve.
And these weren't simple problems. They baked in real-world complexity.
Oh, absolutely.
Yeah.
They use functions with nonlinearities like sine or modulo, complex tree structures, tricky categorical features.
And the really painful stuff too, right?
Critically, yes. The synthetic data had all sorts of patterns of missing values and a high degree of outliers.
The stuff that usually breaks deep learning models.
The very same. So by solving these problems millions of times, TabPFN just autonomously learned robust strategies to handle them. It doesn't need you to clean the data first.
It's already seen every kind of statistical pain imaginable. Okay, so if the model is looking at the entire data set in one go, that's a lot of information. How did they solve the processing bottleneck?
That's a great question. It's a combination of smart architecture and software. First, the transformer itself uses a special two-way attention mechanism.
Meaning?
It attends across the features in a row and then down the samples in a column. This makes the output invariant to the order of your rows and columns.
So I can shuffle my spreadsheet around and it still gives the same answer.
It has to. But the key to that incredible speed is an optimization called train state caching.
Okay.
Normally, the model would have to recalculate everything about the training set every time a new test sample comes in.
Which would be hugely redundant.
Massively. So by caching those intermediate results from the training set, they get huge speedups for the actual predictions. The source says this one trick resulted in speedups of around 300x on a CPU.
300 times faster,
It
just
was-
from remembering its work. Okay, let's get to the performance on real-world benchmarks because that's what really matters.
Well, we hit the headline number, but let's just reemphasize it. Default, out-of-the-box, TabPFN versus top models tuned for 4 hours. The classification speedup was over 5,000 times. Regression was 3,000 times faster. It just substantially surpassed CatBoost, which was the strongest default baseline.
That just changes the whole workflow for a data science team. You can iterate so much faster.
And it's robust. The tests showed it handled two major real-world problems beautifully: uninformative features and outliers.
So if my data set has 10 columns that matter and 400 that are just noise, TabPFN figures that out on its own.
That's the idea. It learns to ignore the noise. And it was highly resilient to outliers, which is a known Achilles heel for standard neural networks.
I think my favorite test was the sample size one.
That was incredible, yeah.
They found that even if you give TabPFN only half the training data, it still performs as well as the next best model using all the data.
Think about what that means for expensive data collection. You could potentially have your budget and get the same results.
It's a huge deal. So we have speed, we have accuracy, but now let's get to the foundation model part. It's not just a predictor, it's a knowledge engine.
Right. And a key advantage here is uncertainty modeling.
Something that tree-based models really struggle with.
They do. TabPFN doesn't just give you a single number like 75% risk. It returns a full target distribution. It tells you how sure it is.
And they showed this with that physics example, the double slit experiment.
Yeah, that classic quantum mechanics experiment.
Yeah.
TabPFN modeled that incredibly complex multimodal light pattern in a single 1.2-second forward path.
On CatBoost.
CatBoost struggled to even approximate it, even with tons of special tuning. TabPFN just handles that kind of complex probability naturally.
And because it's a foundation model, it's generative. If it can model the probabilities, what else can it do?
Two big things. First, data density estimation. You can estimate how likely any given data point is.
Which is the basis for anomaly detection.
Exactly. Fraud prevention, equipment failure, rare medical events, anything that falls outside the expected density gets flagged.
And the other side of that coin is creating new data.
Synthetic data generation. It can create new samples that mimic the real data. This is huge for data augmentation, or, more importantly, for privacy-preserving data sharing.
You can share the statistics without sharing the personal info.
Precisely.
I also found the part about its internal structure really interesting, the embeddings.
Ah, yeah, the reusable embeddings. The final layer representations are meaningful on their own. You can pull them out and use them for other tasks, like clustering.
So you get a cleaner, more useful representation of your data, not just a prediction.
It's incredibly useful.
But what about interpretability? In fields like medicine, you need to know why a model made a decision.
And this is a critical finding. TabPFN supports SHAP values, and it turns out it achieves its high accuracy while learning simple, interpretable feature relationships.
So it's not a black box.
It's much less of one than you'd think. The complexity is in the model's architecture, not in some crazy, jagged decision boundary like you might get from a tree model.
And finally, since it is a neural network, does that mean it can do things tree models just can't, like transfer learning?
Yes, absolutely. You can fine-tune it. You can take the general model and specialize it on a certain class of data sets, say financial data, and get even better performance on future financial tasks. That's a huge step.
Okay, so let's get practical. For someone listening, when should they reach for Tab PFN?
It should be the new default component in your toolkit for small to medium data sets, so up to 10,000 samples and 500 features. If you need speed and high out-of-the-box accuracy, it's a drop-in replacement.
And do I still need to do all that data pre-processing, the cleaning, the encoding?
Much less of it. It's designed to handle raw data, managing missing values, and normalization on its own. But an expert can still add value. If you know a feature has a log distribution, for instance, applying a transform beforehand can still boost the results. It doesn't eliminate domain knowledge.
That makes sense. But what about its limits? Where does it hit a wall?
Three critical limitations right now. First is scaling. Its dominance is proven for that specific size range. How it scales to, say, 1,000,000 rows is an open question.
Second has to be memory, right? If it's looking at the whole data set at once.
It is. Memory usage scales linearly with dataset size, so it can become prohibitive for really large tables. You might just run out of VRAM.
And the third point is a really important nuance on speed. We said it was fast.
It's fast to train, in that in-context learning sense, but that's different from real-time inference speed.
So it's the ultimate prototyping tool, but maybe not for a high-frequency trading algorithm.
Not yet. An optimized production model like CatBoost can make a prediction in maybe 0.00002 seconds. Tab PFN is slower for that kind of high-volume, low-latency use case.
Okay, so it's a tool for rapid development and modeling, not necessarily the final production pipeline.
To sum up, Tab PFN is really the first truly successful foundation model for tabular data. It used that massive synthetic universe to discover its own highly efficient algorithm, and it has fundamentally challenged the two-decade dominance of tree models.
So we've shifted the goal from writing code to designing the ideal training data. What does this meta-learning approach mean for the future, beyond just spreadsheets?
Well, the sources mentioned creating specialized priors, these synthetic universes, for other data types, things like complex time series or even neuroimaging data. And if an algorithm can learn to solve general spreadsheet problems today, the really provocative thought is this: what hyper-specialized self-learned algorithms might be next? We might be heading towards a future where algorithm design is no longer about writing lines of code, but about perfectly defining a problem space, and then just letting a foundation model figure out the best solution on its own.
Letting a simulated universe write the code. That is a fantastic thought to leave us on. Thank you for guiding us through this deep dive.
My pleasure.
We hope you found this deep dive valuable. We'll see you next time.